Welcome back. Today we're going to be talking about the section 2.4 topic of a library of functions. We already did some of the preliminary work on this by discovering all of the properties of the different base functions, and what we're going to do now is we're going to work with those functions a little bit and find out some of the ways that we could think about them in order to give us a little bit more information on how to do them, how to work with them, how to graph them. The first one that we're going to look at is writing a function. And so what we're going to do in this example is we are going to write the linear function for which f of 1 equals 3 and f of 4 equals 0. And so what we need to understand is this is simply a notational issue. And so really what this means here and this means here is these are pieces of information that are going to give us a lot of insight into what this function looks like. And so what we're going to do here is I'm going to just rewrite this and help you think about this a little bit more. This is really my x. 1 is my x and 3 is my y. And so what I really have here is a point on this function, or in this linear function, of 1, 3. And here we have another x and another y. And so we've got 4, 0. So what that gives us is the ability to use these to write a linear function. And so what I can do is I'm going to go ahead and find the slope between these 2 points. And so I'm going to do 0 minus 3 over 4 minus 1. So I've got minus 3 over 3, which is minus 1. So my slope is negative 1. This is good because now I can simply work with either of the ways, point slope or slope intercept form. I'm going to choose point slope form. And so I'm going to do y minus y1 equals my slope times x minus x1. And the beauty of this is now I can pick either of my points, and I'm going to go ahead and pick this one because it's got a 0 in it, and I think that that's going to help me out in the long run. But if I pick the other one, it wouldn't matter. I'd get the same answer. And so as I plug this in, I'm going to get y minus 0 equals my slope times x minus 4. Let's clean this up a little bit. Y minus 0 is just y. My slope is negative 1. I've got x minus 4, and so I end up with y equals negative x plus 4 because I'm distributing this negative 1 to both of these. And so this is my function that maps to both of these points. So that's how we work on that one. If I'd have done it with the other point, it would have ended up the same. And I could go ahead and graph that if I wanted to. Next example is graphing a piecewise defined function. We've got a piecewise defined function here that is f of x equals 2x plus 3 if x is less than or equal to 1, and negative x plus 4 if x is greater than 1. And the way that we need to approach this is to graph the two functions and eliminate what we don't need. So I'm going to start with this first one, and I'm going to graph it in green. Remembering the process for graphing these, of course, I'm going to graph my y-intercept, which is 3, and then I'll use my slope of 2 to find my next point. So go up 2 over 1, and then I could go down 2 and back 1, and that's going to give me enough points to connect my dots. Well, I have to now make my decision about my domain, and so because x is less than or equal to 1, I've got to go to x equals 1, and that's this point here that I'm defining in red. And it could be equal to 1 for this function, so that's a full dot, but it's got to be less than that. And so everything greater than that, I'm just going to erase here, and I'm also going to erase my points where I did my slope. Okay, and so this is this blue half of the function. Okay, this is what I'm circling right here, is this part right here. Because it's that whole graph, 2x plus 3, just when x is less than or equal to 1. On my second function, we can define it in red, I'm going to graph it like normal. So I'll go up to 4. Let me use purple here. I'll actually use purple. And I'll graph my y-intercept, and I'm going to go down 1 over 1. And down 1 over 1. And so my function is sort of looking like this. except now I need to work on this part right here. This x is greater than 1. And so what I need to look at is, where's 1? There it is. And so I know I need to erase everything that's less than 1. Okay? And so my function is now defined by just this purple part. It looks a little bit messy, but one other thing I need to take into account is the fact that this is not an equal to, so I actually need to erase this point right here at 1, and it needs to be an open dot because this graph is not equal to. And so what you're going to see is this piecewise defined function is literally called a piecewise defined function because there are 1, 2 pieces that make up this function, and they're completely different. But this is the whole graph of this. This purple would keep going, and also this green would keep going to make up this whole function. And so that is how you graph a piecewise defined function. Graph one of them, erase what you don't need. Graph the other, erase what you don't need. Okay, and make sure that you're looking at your signs to figure out where it's less than or equal to, those kinds of things. And so the trick to graphing a piecewise defined function is 2 parts. One, we're going to graph each function normally. Okay, so graph them normally. And that's going to allow us to use the intercept, the y-intercept and the slope just like normal. And then 2, erase what doesn't fit. Okay, so use your domain to define what doesn't fit. That's the x is greater than 1, x is less than 1, etc. So you're going to graph each function normally and erase what doesn't fit, and that's going to allow us to graph these piecewise defined functions. Okay, guys? Thanks for watching, and we'll see you next time.